So Linux API. What is a Linux API? First, let's talk about what is a Linux. What is the job of the kernel? So the kernel has jobs and privileges. Jobs are like it has to create a level playing field for all the processes that runs on the kernel, all the user processes. It schedules them, make sure that they are getting the same amount of CPU time. The other job is to manage hardware. So the kernel's job is memory, storage, network cards, anything that you can plug into it, any kind of hardware. It sets it up and makes it available for other processes. Privileges. It has this is actually coming from the architecture. So the CPU can have I think it is called rings in CPU terms. So there are things that like touching directly memory can be done in ring 0, which only the kernel can render. And your user processes ranks in, I think, ring 3. And the user processes don't have those kind of privileges that what a kernel code can do. So just imagine that your process does something, some interesting calculation, but then it wants to either print out the result to a screen, or save it to a file, or send it over the network. For all of those three things, it has to interact with the kernel, because the user process doesn't have rights to touch these directly. So what is the Linux API? The Linux API is think of it as a bunch of functions that is an interface for the user processes to interact with the kernel. You can ask the kernel that please write this string out of the screen. That they do this through this API. You can think of it as functions. There are around a little over 400 of them, and they are not the similar functions than in your main programming language, probably. So, like, but they are wrapped inside. So let's talk about one concrete example. For example, in the C language family, you interact with the system calls usually through libc. Libc is a dynamic library, and it provides C functions with the same name as you can find, same name as the system call you are calling. That's the name of also the C function. But the C function is not is the system call. It just provides a nice interface for you to be able to call a system call like a function. A system call has a different calling convention. I go into it a bit. So a system call is basically just a number, an integer or a long number. So like 52. Every system call has a number, and it accepts parameters like a function do. But for those parameters has to be sent to the kernel in a very specific way, like put the first parameter to this CPU register, the second one here, and things like that. The C library does this for you. It takes the function parameters as it is done by C, and then converts it to the way how the system call expects it to get. Then it calls an instruction, probably it's called syscall instruction, and then it will switch to the kernel, and the kernel can pick up the parameters. But thinking about the system calls as functions is perfectly fine. And most languages actually have an interface to call these system calls. Why is it important to know about it? Well, there could be multiple ways to think about it. Multiple scenarios when it's important to know about them. One is obviously debugging, and I will show plenty of examples of that. And the other way is to know them is that this is not written in stone. The system calls are very stable in general. Some are like 30 years old, and if you use them, then you can make sure that your code will compile probably 30 years later as well. But there is also innovation going on in the innovation in the one of the direction is to actually avoid system calls, because they have a cost. So all these bookkeeping I described previously, and also the cost of switching to kernel from user space to kernel space has a cost. It takes time, and the innovation happens in a way to not have to do this system calls too often, or even have 0 times when you have to do this. I will not talk about that in this video, but this is where it gets really interesting for me. Okay, let's show some system calls first, and before I talked already too much. So I have a very simple makefile here. I just want to quickly show this is not what I want to talk about. It just can compile C, C++, Rust, Go. Okay, what I want to show first is that you probably have a very good mental model in your favorite language, programming language, about the standard library of it and the list of functions that you can use. So when you encounter a problem that you want to solve, you can apply that mental model there. And I want to show that even though you can have a very different programming languages, and like the sample hello world looks very different in all of them, they will all turn out to be eventually to the same system call. This is what I want to show that these are the main building blocks of the user process programs. Of course, let's start with C, because what else? I will include a few headers, a bit more than we need for a simple hello world, because I will use this program a bit more later. But nothing serious. STD. All right. And we'll just call printf. Let's call hello simply. And this is one of the main tools. Let's check whether it works. Yeah, it works. So one of the main tools for discovering system tools and debugging and to have fun is called Strace. Strace, yeah, let's use Strace. So what we see here is that Strace run our code or our binary that we asked to run, and as it ran, it's set between the system calls between the kernel and your program, and it recorded every system call that it saw. So whenever this barrier was traversed. Well, we see a bunch of stuff here at the beginning. Let's call this some kind of prelude. But so let's start at the bottom, because what we are looking for is the hello. When did we write it out? And we can see it here. That it was written out by the system called write, and we can see the string here. We can see a 7 here. 7 is the length of the string that we actually sent. This is actually the output of the program itself. So with Strace here, how we invoked it, it intertwined with the Strace output. We can separate the two with Strace -o, and then we can send the Strace log to a file. But we can just ignore this here. At least we see that the write was actually the system code that wrote hello out, and we can see a return value of 7 here, which says that we wanted to write out 7 bytes, and it wrote out successfully 7 bytes. This one here is a file descriptor. we run this program through Bash, and Bash we inherited 3 file descriptors from Bash, from the parent process, which is 0 is always the standard input, 1 is the standard output, 2 is the standard error. Yeah, so these kind of the write, it works with file descriptors. So we at least this part is pretty easy to understand for us, because this is what we were looking for. Now what the hell is the rest of these things? Okay, we can see an exec v, which was basically that I think this was Bash that called. This is how our hello binary was called to run in a new process. We can see a brk call. Brk is a memory operation, one of the way to get memory from the kernel. Calling it with null actually just returns the current break line. I have a page for this to understand what this means, although this is not super important now. Just a moment till I can find it. Yes. So this is the standard way how I like to think about it. So here we can see this is the memory of the process, of the virtual memory of the process. So this is not really what's happening in the memory, but this is what the system lies to our processes, how it looks like. So these are the high address of memory, and our stack sits somewhere here, and it grows downwards, and the heap grows upwards. And this is not fully true, but about this line we can think about as like the break line. And with the brk system call we can increase that line. So if we ask for a bit, so with brk null we got the current address of this line, and if we don't send the brk null to it, but an direct address, then it will move this line a bit above, and we can use the memory there. This is how I like to think about it. This is not fully true, this picture, especially not for other languages. All right. So here it just asked for the current line. I don't know this one, but we could find that, but that's not my goal to fully understand every line, just to get a glimpse of it. We can see a few files here, SO files, so that means some kind of dynamic libraries. So let's check what kind of dynamic library. This is just a hello world, but it was already uses a few dynamic libraries. One of the most important one here is the libc library, which I think I covered this before. So libc is the library that this is a helper for calling the system calls. So I think Linux encourages you to always call system calls through libc, and you can actually circumvent it. You don't necessarily have to link to this. I think I will show that later. So you can actually write a very simple code just with the number of the system call for write, putting everything together for the kernel to pick it up and call the syscall instruction, and then you don't need the libc. Okay, so it opens some files. fstat is about getting some data of it, all kinds of data from an open file descriptor, like what permission we have for that. You can have the size of the file logs, a bunch of stuff. I can't keep that in my mind. mmap is another memory allocation system call. It actually can do a lot of stuff. Originally, this means memory mapped file. I think that was the original reason. So you can, what this means is that you can open a file and map it to your virtual memory. And then afterwards, you can read from the file by just reading from the memory where you mapped it. Or you can write things to it, and that will be reflected in the file itself. This can be handy to use memory operations for file operations. But it can also do memory allocation without any files. And I think this is the main method nowadays how you can get memory, not via BRK. But you can combine the two, as we can see here. So it looks like that it opened this file, mapped it to our memory, then closed the file. It also opened the libc. It read a bunch of things from it. I see an ELF here, which is the binary format of the executable on Linux. Yes, again, we see the similar dance, fstat, mmap, and it maps it to different places. I have no clue what this does, but we don't have to understand everything in detail here. Okay. Here we can see some memory allocation. So calling brk null, we get back the current address where that line is, and then we ask a bit more. It is almost the same, but a slightly higher address, and then we exit. Okay, let's take a look at in different languages. We won't go deeply over the strace log of all of them. I mean this deep. So C++ is in the same family. Actually, it's in the same compiler family. So we can expect to see a very similar output. But the code looks different, of course. So end means that it will print a new line and also flushes the string, if that makes any difference, we will see. So hello CPP, it works. Let's strace it. And let's again start from the bottom. We can see the write system call. This line is exactly the same as it was for C. So if just looking at strace instead of the program code, it actually simplifies in some sense simplifies debugging, because we can really see what it got translated to. Every code must be translated to system calls for these operations. It doesn't matter what kind of language you use, it will be translated to these. And it looks very similar, although a bit longer, and we can see other libraries like the C++ library dynamically that it is attached to our process, and we see a similar dance, how we are putting that into our virtual memory. And yes, let's take a look at a very different family. Let's take a look at Go now. Package main, I never know whether this doesn't need semicolons. All right. Hello Go. Okay. Let's first the Go program now. Again, to start at the bottom, we can see that the write call, the single line that we actually wrote ourselves, is the exact same system call than for the other programs. Here above, it's very, very different. We can see a lot of sig things here, and I think most of these means that yes, it goes over all of them. I think Go runtime registers its own signal handler for all signals. It wants to handle them itself. By the in the C family, we saw that it didn't do this, so it took the default action for each of those signals. Yes, mostly this is about signals, and it calls this file hpmv size. I'm not fully sure what this is. I have a guess, but probably that's very wrong, so I would rather not even say it now. But what we don't see is shared libraries. So let's Go. Not a dynamic executable. So we can see that Go took a different approach. It doesn't link to libc. Apparently, it doesn't do that, and then that means that it calls the system calls directly, not via libc. In the C family, that's not how it looked like. So even just looking at Strace like this, we can uncover things about the Go runtime. Let's take a look at Rust. Okay. Let's print it. That's a macro. Right. Okay, and let's trace it. Again, start from the bottom. Now we can see more interesting stuff. Syscalls. Anyway, we can see the write call is the same. That's the line we wrote. The rest is Rust stuff. Syscall stack. So it actually remaps the stack. This call. I did not know this about Rust. I don't want to go deep into that. This is also interesting. What else? It also catches a few signals and sets its own handler to it. So this is the Rust runtime, but not as much as the Go one did. And we see that it uses the libc library, so the similar dance to setting up the dynamic library to it. Yeah. Okay, before we move on, how can we read a bit more about these system calls? Because I was just talking about them, but what did not really said how can we know it based on the name? I mean the names of course help a lot. So whenever I'm looking for something, I always type man because I forgot which section has what. But we can see here that the second section has all the system calls. So we can call like man2 and write. And here we can read about this system call. This is actually about the libc function that wraps up the system call for write. But in Linux these are nearly exactly the same. Let's check fstat. Yeah, it's a family of system calls. they have a different arguments, but they all return the same stuff. It's a stat structure. Can we find it? Yeah, here is the stat structure, so we can see what kind of data it returns. Yeah, so you can go into into these its details through the man pages. There is another one called Syscalls, which has a more overview of all the system calls. We can get a full list of them, and can also see which kernel version these appeared. Yeah, this is a funny way that we have clone 1, clone 2, clone 3, and so forth. And also there are some good web pages that are easily searchable. I will later show one of them. I think I will attach those links to the below the video after it. Okay. What next? So this was only a hello world, because I wanted to. I think we learned a lot just simply by looking at hello world. But let's add a few more stuff to this course. So printing to string. For example, let's open a file and write something to it, and let's see what kind of system calls they are. We achieve this, and maybe also sleep one because that's easy. And memory allocation. That can be also pretty interesting. But what happens when we just allocate memory? So let's start with the file. See, this is fopen. Yes, let's check if that was successful or not. I don't like to leave code that doesn't handle any errors, even if this takes time. Don't open file. Yeah, it's a little more typing, but I sleep better this way. All right, then we need some kind of data that we want to write out. We will write out only hello to the file. And in order to write out the size tip, we will use the fwrite function. This needs the data. So how fwrite works in C is that this can actually fail in multiple ways. So the written data can be less than what we asked it to write out, but no error. Just we have to write out the rest in another fwrite call. This can happen. Also, we can it can fail. Of course, it can write out less, and then because it fails, we can check that it error or anything. Anyway, if in normal circumstances, no matter how big the file is, maybe if it's less than the free memory, then this will not happen. So you don't have to write a loop. And this is where I compromise now a bit, because the code would be a lot longer. So I'm just checking if we wrote it out. Only right. Okay, so after this we have we have a file operation. We're opening it. Let's close it as well. The funny thing about closing the file that it can fail. Yes. And what to do then? Yeah, that's a good question. This actually is most likely indicates that, well, of course, I know when it can fail, but well, you have a big problem then. You can't handle it in code. So, nah, anyway. But if you call fclose twice, it will surely fail the second one. But that's not the reason. If you have a disk problem, or you know, there is not enough space, and you with fclose you are flushing out the file, and that can fail and things like that. Yeah, let's leave it. So okay, file operation. Let's hope I didn't make a mistake, and let's trace it. Alright, so this is the write call which we left in earlier, and now we can see a new one called openet for the test.txt, and this is, I think, pretty readable coming from C. All the flags we set up. It also sets up the permissions to the file. Then it fstats the file, which you check what it does, and then it before writing it out. And it calls the same write system call to write out the text, hello. And we see a close function too. Basically, the open, read, write, close, these are the most basic Unix system calls. These are the oldest ones. Many things are abstracted as a file. So you can put a file in the phrase on top of many things. Let's just quickly test. Yes. Okay, what else can we very quickly add to this? Memory allocation. That is interesting. Oh, let's add the sleep one. Then let's try some memory allocation. Malloc. Let's allocate 50 bytes. Right. I lost. This is the longest call I've written today. All right, let's see what happens. Let's trace it. So what we changed, we added a sleep. We saw the sleep happening, and we also allocated some memory. And we didn't free the memory. I will get back to it. So, but we can see the sleep here, that it uses the clock nanosleep system call. Okay, we can probably read upon that. Clock nanosleep. High resolution sleep is specifiable clock. Yeah, good to know. But we don't see anything about the malloc. So we write it to the file, close the file, slap, and it should be somewhere here, but it didn't. Let's change a few things here. First of all, maybe let's sleep here instead. And don't forget to free the memory. Okay. But we will make one bigger change. Let's increase this memory a bit. And let's see whether that makes any change. And it did. So we increased the memory, and we see now an mmap call. The mmap, we move the sleep a bit between the allocation and the free. So we can see this in pair now with mmap and munmap. So what changed? What changed is the size of the memory that we requested, and we can see that this is actually not the same what we requested, but this is just it set it up to the nearest nearest page size. The page size is, I think it's 4K, the memory page, or 8K. I'm not fully sure. So it just allocated the right size of memory. But why didn't we see any of this in for the smaller size? Well, as I mentioned, the system call has some costs to it. So it's very common to allocate small chunks of memory. And the malloc implementation optimizes for this. So it doesn't go to, it has its own chunk of small memory chunks that it can hand out to your process without going to the kernel. And that's a very big speed up, because it's very common for programs to allocate small memory and deallocate them. Allocate, deallocate. This is super common. Allocating big memory and keeping it is also common. But it's not common to allocate big memory and free it. Allocate free. That's not common, as I understood. So yeah, and maybe a bit about malloc. Malloc is a very complicated function. It looks like, you know, just a simple thing which you have like 4 variations of it with the free as well. So realloc, calloc, malloc, free, and yeah, I think maybe that's it. But this function has to be very well optimized in different scenarios. We have a single-threaded program, but it should work really well for a multi-threaded program with 100 threads, and each hammering malloc, like you have a server that allocates a small string for each call. It's so how could malloc work? So it's easy to think about many naive implementations. For example, maybe it keeps track of the memory it handed out to the processes and in a structure, and then threads are coming asking for memory. Then nearly if it makes a change to that structure, then you have to look somewhere. So that's immediately a naive solution which doesn't scale, because if it gets hammered by multiple threads, then there's a contention on that lock. So that's not good. Another naive implementation could be, okay, let's have a different bookkeeping for each thread, and maybe use a thread local storage for keeping to do that bookkeeping. But that sounds good, because then it's multi-threaded, but then you have a problem like why couldn't one thread allocate memory and then hand it over that memory to some other thread, and the other thread will call free. it's not in that same thread local storage. Anyway, where I'm going is that malloc is actually a pretty complicated function, and there are different implementations for it, and different they are good in different cases. And of course, there is a generic one as well. And malloc uses internally, I think, nearly always mmap, but maybe brk as well. I will look this up later. Okay, so we see memory allocation files. Let's do some debugging. So I started a mystery process here before I started recording with the PID of 195, and I want to show that Strace can attach to our running process, and we can actually look at it, what that process is doing. So the output is not much, but we can see an except for, and somewhere in the middle of it, because we just except for on 3. 3 is a file descriptor, most likely. Okay, let's take a look at the main page of except for. Accept a connection on a socket. So it is waiting for something. So it has an open socket. So what can we do? There are multiple ways to check the open sockets for a process. One of them is netstat, LSOF is the other one. Let's use LSOF now. So we can with this we can check a process's open TCP and UDP and maybe Unix socket connections. On 95. Yes, so here we can see that it has a TCP open on this port. It listens on that port. Let's go back to Strace, and in a different window, let's connect to that port. And let's see whether we will get anything here in the Strace as it is running. So we can do a netcat localhost to connect to a TCP port. I think it was 4005. Okay. Yes, something changed. So the accept, we can now see the full accept call because something because it was successful and something connected to it. It got back a new file descriptor, and now it is in a poll. The poll is a way to check for a list of file descriptors whether something is happening, and let's send a message to it, and let's see what happens. We can see that the poll returned, and it said in the return value also that oh, I don't know this actually what this is, that it looks like it returned not just an integer, but also it returned a struct that says that the file descriptor 4 has some event, and you can call read on it. And then it called read on it, and it was successful. It got the hello, and it went back to polling again. And it also wrote out what it got, which we don't see here because this is not our, because we are not attached to it. So we see only the Strace output to it, but the standard output of this process is not redirected to here. All right. Let's close this. And when we close the connection, this one died. So we did not close it properly. You see it closed the 4, which was ours, and closed the 3, and closed it again, and it failed. This is funny. I don't know why it closed the 3. I don't expect this to be an error in the code. I think it closed it for a reason, but I have no clue why. Never mind. So the mystery process was actually a netcat as well. So it was just like this. This was our mystery process. Maybe we can Strace it as we started. And yes, so also a bit of a prelude for opening the dynamic libraries. It creates a socket, sets a few things, binds it, listen to it, and accept. Yeah. Now we can Strace actually Strace itself. So how does Strace work? Here now we should redirect the output to a file because it would be a really mix of 3 processes: Strace, and again what we are running. So let's redirect the outer Strace's output to a file, and our goal is simply to get out the meat. How would you implement your own Strace? Okay, let's take a look at that Strace file. It's pretty big. So we are just skimming over this output and try to search for something that we didn't see before. And now we can see something called ptrace. So let's check that ptrace system call. It's called process trace. So this system call provides a means by which one process may observe and control execution of another process, the trace. And we can see the arguments to it. So just using the pre-trace system call, we would be able to implement strace ourselves. It's just a system call. That's the meat of it. How does lsorf works? We can take a look at strace lsorf. Let's start the process first. All right, I went to this screen and alright, let's do an strace minus lsorf text and lsorf minus a. And of course I don't know the process. Damn it. So we run 1530. lsorf all right, and let's just try to skim over that one as well and try to find out what kind of things it does. Yes, we can already see some new stuff. And now this is interesting. So it tries to close a bunch of stuff. I can only guess at this moment what that means. I think this is on purpose. Maybe this is some way to go over different file descriptors, sockets, and see whether they are open or not. I can only guess at this moment. But it was pretty weird. What else do we have? Can we grasp something? Sets alarms. Okay, we missed these 5 and 6 file descriptors. Let's go from the bottom now. Because etc services, this is a list of it lists common ports for common services. Okay, now something interesting. So it actually works the proc file system. Yes, it checks many things there. So let's check what we can get there. So we can go to ls proc, and what was the NC is on 1530. So let's check this one, and we see a bunch of stuff here. So proc file system is basically, it's a view to the kernel's memory about specific stuff formatted for us, for end users. So we can cat some files from it, and look. Of course, we can investigate with ls as well. And for example, this one has the fd folder, and maybe we can get more info like this. Yes. So just going to this process ID in the proc folder and go to the file descriptors, we can already see that it has something open out of the default standard input-output error, and the third one is a socket. It is a listening socket. Yeah, interesting. Maybe we can. I don't think we can cat that. But Maybe we'll break it. Okay, never mind. So this doesn't work. Maybe we can get other stuff here. Yeah, I see a syscall here. What does it do? Okay, I think this worked, but it printed out a bunch of things that I have no clue what this is about. But man pages again. So man proc can help, and I think you can just search for syscall here or FD. Now this is interesting. So this exposes the system call number and argument registers for the system call currently being executed. So that means that what we see here, at least the first one, this 288, should be the, where is my Strace output? I don't have it, but I can attach to it. And I will finish the sentence after that. Strace minus P 1530. So that 288 should be the except for number of that system call. Now I don't know a way yet how to get these numbers actually here in the man page. It's not listed in man syscalls. That's for sure. There's except for. Why I don't have it? Because I went too fast. Yeah, it's here. We don't have the numbers here. We don't have those numbers here either. Yeah, but there are some good pages for this. So let's try to find those. I will attach these to below the video after this. So there are some good pages, and this is one of them. You have different numbers for 64-bit and 32-bit kernels. And for 64-bit, so that the 288 should be the except for. And yes, that's what we see here. Okay, I think this is interesting. Hey, it's not very useful for us at the moment, but yeah, clearly there is a translation between the proc syscalls. Yeah, you know, if the proc syscalls would actually say except for, then it would speak the same language on all the places, but it doesn't. So yeah, I don't know yet how to map directly the numbers to the system call names. All right, what else? I think this is basically what I wanted to show. So let's try to summarize it. So we have around 400 system calls. They are quite stable, but innovation is ongoing about that. And I will probably talk about those in later videos, because those are very interesting for me. Innovation is more like about how to avoid system calls, how to make it more effective for very heavy traffic applications, and yeah, how to circumvent this. So I said that you can't go to the network card without talking to the kernel, but that's actually not true. Some network cards and there are some options how you can, as user process, can directly interact with the network card. Especially to make it, to use the hardware as to the edge as possible, to squeeze out every performance out of it. So I was lying a bit in this regard. There are ways to do this. It's not common code, but it's pretty interesting, and you need the hardware for it and specific modules. So why it is useful to know about not Strace. Strace is also useful. It is because to know the basic building blocks of a program, and or maybe one thing I also want to say is that disassembly and Strace is not the same thing. So Strace only sees when your code interacts with the kernel through that interface. And I think that's a very good filter, depending on what your goal is when you are debugging. I used it. I used it a lot. Disassembly shows you everything your code does. For example, if it calculates a hash, then that will never call any system calls. But it will show up in the disassembly. We can do a poor man's disassembly like this. Then we can see what's happening. This is very different. These two tools are orthogonal and can be useful in different scenarios. So I have etc here, but let's just quickly show a quick. And I killed it. I just want to show the beginning. So no, this is it. I'm looking for a line here. Lots of few text. And of course I can't find it now. Okay. Okay, I see it here. So many years ago there was I heard about a bug at work. So there was a CI/CD setup, and it was a very complex one. It used Docker Compose inside the VM, and one of the members of the Docker Compose was etcd2, I think, and they had a problem with it, that it stopped working after some change, and I heard this for 2 weeks. And it caught my ear, and I asked them what's the issue, and I did not have access to the machines, but I asked one of the person to please run Strace during the runtime startup when it fails, and I got a file similar to this, and I saw these val files. That's why I did this Strace now. I think this is write ahead log. Anyway, it's not important. So what I saw is that this is a etcd3 now, so it works a bit differently. I think it tried to use file lock system calls on that file, and that failed. That's what I saw in the message, and that led me down. This is what triggered my investigation, and I show it to the others, and they had different ideas what could go wrong, because it was a very complex setup. They had very good reasons to think that this is not the right direction, but I took it at home. As I said, I did not have access to the machine. Just took home this log and started to dig into etcd source code, what they are doing with this file. And it took me a few hours to figure out that they are not running the latest one, so it is the earlier one. And then I digged into the Linux kernel, especially for this copy on write storage part, and how they implemented it, and what's the history there, because it was relatively new at that time. And I immediately found that they had some bugs at the beginning. But it was really hard to chase down what was the kernel when this bug fix was merged into it. Then I had to find, all I knew that these servers, the CI/CD servers, ran CentOS, and I had no clue which one. So I looked at different CentOS versions, downloaded the source code, looked at the different versions, the kernel versions they have. That didn't tell the full picture, because CentOS, how it works, it says that I'm kernel 1, some kernel version, but they actually pull in bug fixes from later versions. So it took me a while to actually go to the code, go to the lines in those kernel codes, to figure out which CentOS version had that fix and which didn't. So after I had this, the next morning all I asked is that okay, what is the CentOS version we are running, and I was lucky. This was the case. So we ran an old version of it, So we just upgraded to a newer one, and this was fixed. I was very happy, of course. So all of these debugging thing started with an Strace. So it was very useful. Oh, one bonus thing, because I forgot something. So we see that NC calls, NC uses poll and accept and these kind of system calls, and read, of course. And I want to check what does a similar code in Go do, because we saw that Go works differently. So maybe they will surprise us, and I think we can learn. This is just a few minutes. So let's create the server Go. I got this snippet from a friend of mine. So in case this doesn't work, Bart, this is all your fault. Okay, this code just opens. So Go is very good in HTTP, of course, and this just creates a HTTP server and sends us this welcome to the new server message when we interact with it. That's the idea. Let's trace what's happening while we are doing it. Now we immediately see that instead of poll, it calls epoll. And this is what I wanted to show immediately, that this is a newer generation of poll, and there is actually another way, and a more newer way how to poll things, yeah. So depending on your programming language and what kind, when it was written, when the standard library was it written, and how up to date it is, they might use a newer, a better way to do things. Let's talk to it quickly. I think it was the port was, nope. Yeah, oh, of course, at least we know that this was the port that was used. So let's connect to it. It's HTTP. Hope I can get it right. Host, localhost, and okay, 2 enters. Okay, we got the response. That's good. And what happened here? And it didn't die. That's also nice. So let's see what was here. Where is our epoll, where the whole thing started? You can see some epoll here. Yeah. Create, read. So it still uses accept at some moments, but it looks differently than how our netcat code Strace looked like. One thing I don't see here is when it wrote us back that message, the welcome to the new server. I don't see it here immediately. Maybe I'm just blind. That's just the Go thing. Created the socket, epoll create. Yeah, it read from it. I don't see a single write call here. That's very interesting. So Strace can actually follow the threads of the process. Maybe it creates a new process. That might be, but that sounds not okay for me. I mean, this is not Apache. Anyway, I don't have the answer here why we don't see that write call. Maybe it actually uses 2 processes and we don't see the second one. the child process. Or I should just read these line by line to figure it out. Anyway, I will not go deeper into this now. Thanks for listening, and that was all for today. Thank you.